Hi there, we're Team in MPC We Trust, and I'm Bradley Cage.
I'm Eric Howe.
I'm Kyle Archer.
Okay, so for the system we have is an example from MATLAB, and we have environment pilot and vehicle system model, and we're going to run through it. And for the pilot, we have the altitude command and the speed command connected to the control system for control, or MPC control. And for aileron elevator rudder and throttle doesn't really do anything. And then for the inputs to the vehicle system model, in the avionics is where the MPC, our control is at, and it's a closed loop system that goes into vehicle. Okay, and then in here, the guidance doesn't really do anything. Here it's just showing the components. And then here the autopilots, we have our MPC block diagram. And Bradley, do you want to talk about the design?
Yeah, so getting into the MPC design, we really have to design the MPC based on the number of inputs and outputs we have into the systems. So currently we have a 2-input, 2-output system where the inputs are altitude and desired altitude, desired speed, and then we tune those with a variety of different weights to then actually get different responses. So here's just a quick overview of the vehicle model as well. It's a very fleshed out example, which we're lucky to have in the fact that we can really focus on the control system design rather than the dynamics of an airplane. We also built some instrumentation just to be able to visualize everything a little bit easier as we're moving into a visualization. So this would be the first one of our cases. So just to give you a little bit of an overview of what's happening here, we have 3 graphs on the top. The graph at the top left is the reference or the desired altitude versus the actual altitude. The graph in the middle is the desired speed versus the actual speed. And the graph on the right is the throttle and elevator response, which just an output of what control the system is taking. And we have our gauges on the bottom and our flight happening on the bottom right. Now, we have 4 different scenarios that we're going to run through. This is the first of those, which is a constant altitude of 2,000 meters and a constant speed of just under 215 knots. We can see that the way that we've tuned the controller, we actually get really nice steady state performance with both altitude and speed. There is a slight error in altitude, but we're very focused in just around that 2,000 meter mark right now, so the error is less than half a meter, it seems. Talking a little bit about how we actually went in and controlled the systems and built the controllers is an interesting conversation. We had to really learn a lot more about how we could pose our systems so that MATLAB's default Kalman filter could actually handle the the very nonlinear system that is this airplane and the control that we were trying to apply to it. Actually, we're transitioning now to the next example where we'll have one of these parameters will be changing. These parameters change and have different importances and different aspects to which they need to be given different rates, and we have both physical constraints on the throttle can only go so far, the elevators can only extend to a certain degree. But when tuning the controls, we didn't really find that the absolute or sort of the extremes made as much a big of a difference as limiting the rate at which things could change. So here in this example, we have our speed changing while our altitude remains constant, and speed was fairly resistant or still fairly robust even when we changed at an infinite or minus infinite rate. But as we'll see in some other examples, the elevators really needed to be limited so that the plane wasn't doing flips, going around, and not staying steady. And this is actually a later implementation of what we did. We started off with a bit of a different model, and I'll let Kyle talk about that for a bit.
Initially, we started off with a similar model as this one,
Here's another example created by MATLAB. Some of the issues we ran in, the models are very similar, and a lot of the things that were in that model are applicable to this model. And some of the issues we ran into were the system being quite unstable. The system wanted to overcompensate for not being in the right position by using too much thrust. But ironically, that would cause the system to become even more unstable. So once we introduced the constraints, such as limiting the throttle and the rudder angles, the system actually behaved much better. We also had a bit of an issue with overshoot and oscillations, but repeatedly tuning the system and adjusting for the robustness and aggressiveness of the system through MATLAB's MPC designer, we were able to minimize the steady-state error and oscillations. However, if you look at the plots, we still do have some overshoot. Fortunately, that's not too big. It's about maybe 5 or 10 feet or meters over the span of 10 or 20 seconds or so, so it's not too noticeable. Initially, we wanted to also control for lateral position and do also like X, Y, and Z, as well as taking off and landing. Unfortunately, the initial model we started off with, we found out was not completed entirely, and that would not be possible. So when we moved to this model, we also tried to control for lateral position, but found that we ran into a lot of issues with the solver trying to fly the plane inverted, even despite applying constraints to it as well. So we narrowed the scope of our project from doing complete takeoff and landing to just controlling it on at a constant altitude or near constant altitude instead of takeoff and landing.
One thing that we really realized in doing this project was just how difficult it is to control such a highly nonlinear system with so many different variables. As Kyle was mentioning, we were controlling other things. We had 4 outputs from our plant and a couple different reference inputs, and the complexity was just really spiraling out. And depending on the sample time, the filters and the design just could not compile. So a lot of learning on all of our parts about the challenges and implications of real-world MPC application.